Hello everyone. Today we are going to talk about rigid body dynamics, BSc Mathematics version. Now, rigid body dynamics is the branch of mathematics which deals with rigid bodies. Now, what is a rigid body? In physics, a rigid body is a solid body in which deformation is zero or so small that it can be neglected. A rigid body is usually considered a continuous distribution of mass. Now we go on to our first concept of this chapter, rigid body dynamics, which is the basic concept of a rigid body, and that is distance between any two given points of rigid body remains constant in time regardless of the external forces exerted on it. Okay. Now we move on to our next concept, which is the concept of isometry. Now consider a function f x to y for a rigid body where any arbitrary point P is mapped to f of P. With respect to the function, we call that function from x to y, which maps the point P to f of P. We call this function an isometry if and only if the distance metric between any two given points in x, say P and Q, will be exactly equal to the distance metric between Fp and Fq in y. Now we move on to the first problem of this video, problem number 1, that is composition of any two isometries is again an isometry. It's kind of easy, so let's do it. Let f x to y be an isometry. Let g y to z be another isometry. So from the definition we know d of x p q is equal to d of y f p f q. We call that equation 1, and this holds for all p and q belongs to x. Now similarly we get that d of y of fp and fq is equal to d distance metric in z between g of f of p and g of f of q. We give that equation number 2, which holds for all fp and fq belongs to y. So equate from 1 and 2, we get the final equation, and hence we prove that the composition of any two isometries is again an isometry. Now we move on to our next concept, which is the concept of orthogonal transformation. Now we know that how isometry, the concept of isometry in R cube can be related to a rigid body, because an isometric function in R cube says that between any 2 points the distance metric will be preserved with respect to time. That's what it says. So similarly, orthogonal transformation by definition is a linear map from x to y, let's say in our case R cube to R cube, in such a way that for any 2 points P and Q in R cube, and its mapping, like P maps to T of P, where T is the orthogonal transformation and Q maps to T of Q, then it preserves the inner product space. That is, the inner product space between inner product of P and Q will be exactly equal to inner product of T of P and T of Q. That is what we call an orthogonal transformation in R cube. Let's move on to our next problem, problem number 2. Any orthogonal transformation in R cube is again an isometry. So we consider an orthogonal transformation T from R cube to R cube, a linear map, such that for all P and Q belongs to R cube, inner product of P and Q is equal to inner product of T of P and T of Q. We name this as equation number 1. Now we define the metric T of P and Q is equal to norm of P minus Q in R cube, which is the distance metric for all P and Q belongs to R cube. Now the distance metric between T of P and T of Q can be written as a norm of T of P minus T of Q, which can be written as under root of inner product of T of P minus T of Q, comma T of P minus T of Q, which is the basic definition of norm, which is again equal to under root of this, and we reach to our answer, which is the norm of P minus Q, which is the distance metric of P and Q for all, and this holds for all P and Q belongs to R cube. Therefore, T is an isometry. So, First we learned about isometry, then we learned about orthogonal transformation, then we learned that every orthogonal transformation is an isometry. Now how to connect these concepts to a rigid body. Before that, let's explore a bit more. Why is orthogonal transformation called an orthogonal transformation? Why is the term orthogonal there? Let's name this problem number 3. Okay, explain why orthogonal transformation is termed orthogonal transformation. Yeah, let T be an orthogonal transformation in R cube. T from R cube to R cube a linear map such that for all P and Q belongs to R cube, and the product of P and Q equal to, and we name this equation 1. Now we know by Gram-Schmidt orthogonalization from every basis of a finite dimensional inner product space, R cube in our case, one can construct an orthonormal basis. So therefore, we say that E1, E2 and E3 be the basis of R cube here. Now by the definition of Knockling's delta, delta ij, which is equal to inner product space of E of I and E of j, which is actually equal to 1 if I equal to j and equal to 0 and I not equal to j. Now let P and Q belongs to R cube. Therefore, P can be taken as C1 E1 plus C2 E2 plus C2 E3, C3 E3, and similarly Q can be taken as D1 E1 plus D2 E2 plus D3 E3, where C1 C2 C3, D1 D2 D3 are fixed constants with respect to points P and Q, arbitrary points. Now, from equation 1, we have inner product space of P and Q equal to inner product space of T of P and T of Q. Now, P and Q we can write like this. For T of P, that is T of C1 E1 plus C2 E2 plus C3 E3 can be written as C1 into T of E1 plus C2 into T of E2 plus C3 into T of E3. Similarly, for Q. Now for the next step, by solving this inner product space, we get this summation. For people who are not understanding this, pause the video and try to calculate this. For there are 3 terms, C1 E1 plus C2 E2 plus C3 E3, then D1 E1 plus D2 E2 plus D3 E3, C1 E1, D1 E1, C1 E1, D2 E2, C1 E1, D3 E3, and similarly we get 9 terms. So it's actually a summation. So hence we get to the next step. Similarly, for the right hand side, we get summation k equal to 1 to 3, summation r equal to 1 to 3, summation l equal to 1 to 3, summation d equal to 1 to 3, ck dl, tkr, tls, the inner product space, which is the one thing that's coming common for all terms. Write it aside. For LHS it is inner product space of ek and el, and for RHS it is the inner product space of er and el. Now, by the definition of Knockling's delta, that is delta rs, we know for r not equal to s, delta rs is equal to 0. Therefore, we eliminate all the terms where r is not equal to s. And so we get to the next step in which RHS becomes into Knockling's delta, which will be equal to 1 for r equal to s. Now, we take all the terms to the left hand side. So therefore, we get summation k equal to 1 to 3, summation l equal to 1 to 3, ck dl, then a huge bracket, summation r equal to 1 to 3, tkr, tlr minus delta kl, bracket close, equal to 0. To people who didn't understand this, what we have done here is simply we have taken the ck dl element on both the sides, common for each term. Okay, so when we do summation, we get the ck dl part in every term on the LHS and the RHS. So we take that common. Okay, and so therefore the summation becomes common, and in the bracket for each ck dl term we have a common term, which is summation r equal to 1 to 3 tkr tlr minus delta kl equal to 0. Now since p and q are arbitrary points, okay, these ck and dl are arbitrary, so we cannot depend on this. So we solve this equation independently of ck and dl. So therefore each and every term of ck and dl, the multiplying factor, which is the summation tkr tlr minus delta kl, will be equal to 0. That is, for each of the c1 d1, c1 d2, c1 d3, all these terms, the multiplying factor for all these terms must be equal to 0 for the whole equation to be equal to 0. Since c1 like ck dl are arbitrary constants. So therefore we get summation r equal to 1 to 3 tkr tlr minus delta kl equal to 0 for all k equal to 1 to 3 and for all l 1 to 3. Now if we look at this, we can see that the terms on the left hand side can be written in a matrix form. That is, if we take the transformation matrix corresponding to this orthogonal transformation or this transformation in R cube, from this equation we get that T k cross R into T of transpose R cross L minus the identity matrix k cross L, you can say, is equal to 0. So therefore T into T transpose, which will give as a matrix of k cross L, is equal to the identity matrix of order 3, which says T, the transformation matrix related to the function or the transformation we were looking, is indeed an orthogonal transformation, and hence the term orthogonal. Yeah, so pretty interesting. Yeah, so let's move on to our next problem. Okay, now this problem we try to find a relationship between isometric functions and orthogonal transformations in R cube. How is it related? We know that all the orthogonal transformations are isometric in nature. But what is the relation between those, and how in the end we'll find out how it's related to rigid body dynamics. Now the question is, we'll prove that any isometry f from R cube to R cube can be written as f of p is equal to f of 0 plus g of p for any p belongs to R cube, where G is a linear map and G is an inner product preserving map. Or we can say G is an orthogonal transformation in R cube. So let's solve this. Answer. Let f be an isometry. So we get equation number 1. Now we define G from R cube to R cube in such a way that for all p belongs to R cube, G of p will be equal to f of p minus f of 0. F is already defined. So we start from the norm of G of p minus G of q the whole square, which is the distance metric. And we take the whole square and we reach to the inner product space, and we solve for 2 into inner product space of G of p and G of q. Now here on the right hand side we get G of p norm the whole square plus G of q norm the whole square minus G of p minus G of q norm the whole square. And since by definition of G we know that G of p is equal to f of p minus f of 0 and so on. And here f minus f of 0 and f plus f of 0 cancel out. And since f is an isometry, we can write that the distance metric of f of p and f of 0 will be equal to the distance metric of p, the point p, and the point 0 in R cube. And hence we get that the inner product of G of p and G of q is equal to the inner product space of p and q for any arbitrary points p and q in R cube. Therefore, G is an inner product preserving map. Now, by Gram-Schmidt orthogonalization, we again take an orthonormal basis of R cube. Now, we have already showed that G is an inner product preserving map. Now, we have to show that G is a linear transformation. So, we take 2 points P and Q. We say P equal to C1 E1 plus C2 E2 plus C3 E3, and Q equal to D1 E1 plus D2 E2 plus D3 E3. Now, we have to show that G of p plus q is equal to G of p plus G of q for any p and q belonging to R cube. So here we start from the inner product space of G of p plus q and G of ei for any I equal to 1 to 3. And this will be equal to p plus q, comma ei, and so on and so on and so on. And hence we get G of p plus q equal to G of p plus G of q, comparing the G of p plus q part on both the sides. Now, moving on, we start from G of C into P, where C is a constant, is a fixed constant, and G of EI, I equal to 1 to 3. This will be equal to inner product space of C into P, comma EI, since it's an inner product preserving map. We have already proved it. And so on and so on and so on and so on and so on. We get G of CP is equal to C into G of P, where C is a fixed constant, and this holds for any p belongs to R cube. And hence we prove that G satisfies the two conditions necessary to say that G is a linear map. And hence, we get our final conclusion, that is, any isometry can be written as f of p is equal to f of 0 plus g of p for any p belongs to R cube where G is an orthogonal transformation, that is, a linear map and an inner preserving map. Now we try to find a relationship between isometric transformations and orthogonal transformation in R cube and see how it is significant for rigid body dynamics in R cube. So we look at the conclusion and some special cases, and then we move on to our next concept, or the final concept, okay? That is translation and rotation in rigid body dynamics, and how is it relative to the isometric functions and orthogonal transformations in R cube. Now for special case number 1, we take g of p equal to p for all p belongs to R cube. Okay, so we get f of p equal to f of 0 plus p for all p belongs to R cube. Okay, so let's say f of 0 is equal to q. So p1 maps to q plus p1, p2 maps to q plus p2, p3 maps to q to p3. Now this, if we see it through a diagram, we can see that it shows pure translation. Now if we take the f0 part, 0, which obviously belongs to R cube, and we get fp equal to gp for all p belongs to R cube. Now g of g is an orthogonal transformation, and hence we can say that this isometric function resembles rotational motion. First we took g of p equal to p for all p belongs to R cube. Okay, it's not a constant function. So we got an isometric function which resembled translatory motion. Now for the third case, we take f of z is not equal to 0. Say f of 0 equal to q, some constant in R cube. So we get f of p equal to q plus g of p for all p belongs to R cube. Now this defines an affine map, physically representing a mixture of translatory and rotational motion in R cube. Also, here we ignore the fact that the orthogonal transformations that we are taking, or the orthogonal matrix that we are considering, has determinant t always positive 1, because negative 1 resembles reflection, not rotation. Okay, so now we can understand how orthogonal and isometric transformations or functions in R cube can resemble translatory, rotational, or a mixture of both of them, that kind of motion of a rigid body in R cube. Now, there's one more thing to cover, that is the universality of translation. Now, the universality of the translation says that if a particular point on the rigid body is translated by q units, then every other point or any other point on the rigid body will also be translated to q units. So Ra vector maps to Ri plus q. We will prove that for any Rj vector on the rigid body, the same translatory motion will map to Rj vector plus q, a fixed constant. Okay, so we take Ri vector dash minus Rj vector dash is equal to Ri vector plus q minus Rj vector dash, and so and so and so, and we get the result. Since it's true for any Ri Rj belongs to the rigid body, therefore the universality of the translation holds. Now, in terms of physics, let's define u vector as the translatory motion of a rigid body, or the translational velocity of the rigid body, and omega vector as the angular velocity of the rigid body. Now both of these are universal vectors, that is, they remain same for all points on the rigid body. We discussed this just now. So by definition, for any point p, the velocity at that point v vector is equal to u vector plus omega vector cross r vector, where r vector is the position vector of p in the rigid body with respect to a base point O. Here, u vector and omega vector are universal vectors, that is, they remain the same for all points. Okay, the only thing changing here for each and every point is the r vector, which is the position vector of the point P, or the arbitrary point taken. Okay, and that's it for today. So we have covered 4 concepts and 4 problems. I'll see you again for the next video. Peace.